You should have your book open to page 301. Page 301, on that page, there are 4 different graphs. It's just going to be easier for you to screenshot from your book than to try to take pictures of the TV. So just have that available. I'm going to go through them one at a time with you and then talk about them, and so we can get a sense of what we're doing here. Okay. Before we get to that, though, I want to talk about some of the meanings of these words up here. Parent function. I mean, it's you think about your existence. You exist because of your parents. Okay. The fact is that all functions, all graphs exist from the basic beginning function. And so that's kind of another way to think of parent functions. If you've ever done any car shopping of your own or built a car online, I'm sure some of you have built a car online, like your dream car that you were going to buy. And they set you up with the basic model, and then you can upgrade, right? You're going to upgrade the rims, you're going to upgrade the electronics, you're going to upgrade the navigation system, you're going to upgrade the tinting on the windows, you're going to upgrade the colors, those kinds of things. It's the same idea. You're taking the base model of the car and you're changing it and tweaking it to turn it into something new. You transform it into something new. We're going to do the same thing with equations. We're going to add things, we're going to multiply things, we're going to divide things, we're going to subtract things to the parent function, and we're going to end up with a new function, the transformation of it. And so what's important is when you see numbers in an equation in a certain way, you learn what that does to the parent function. So this section is all going to be about, here are the parent functions, we're going to do some things to it, and we're going to get a new function, you're going to graph it, and based off of the numbers in the equation, you're going to be able to tell, yeah, this makes sense. It should have moved over, or up, or flipped, or stretched. Okay, and so we're going to go through all those. And the first thing we need to do is talk about what the parent are. So the first parent function, and this one doesn't come into play that much. This is called the constant function. All right. In order to be a constant function, so this is the first one on that page, in page 301, the top left one, we have just a y equals. There's no x. It's just a horizontal line. We've been talking about the horizontal lines for the last week or so. And so the only difference would be is we change the value of the number. So it could slide up, it could slide down, but it'll always be a horizontal graph. So this one doesn't come into play that much. This is the identity function. And this identity function is the basis for all linear functions. They all started off as this identity function, y equals x. And we're going to tweak it, we're going to change it, we're going to add stuff to it, we're going to multiply stuff to it, and every linear equation, every linear function comes from the identity function, okay? And I'm going to show you how the multiplying, dividing, adding, subtracting will impact this parent function to give us the new ones, okay? All right, the next one. Now I'm switching to the next slide. This is the absolute value function. We've been talking about that for a little bit too. Okay, we know absolute value functions look like V's, and so that is one of our parent functions as well. Okay, just the y equals the absolute value of x, the most basic absolute value function that exists. Okay, so that's the V. And it talks about the domain and range and all that stuff, and we know how to find that. The last one that we need to look at, parent function, is the quadratic function. We haven't talked about this one as much, but this is the quadratic, the basic quadratic function, y equals x squared, and the graph of it is called a parabola. And so all other parabolas start off as this, and then we change them based off of what we're going to do with some of the numbers. Okay, so those are our 4 parent functions that we're going to talk about today, and I'm going to show you the different types of transformations to either put them in a different place, to flip them around, or stretch them, or whatever. Okay, and so you should be able to, after this, get a sense of what certain numbers will do to certain parent functions. That's kind of the goal of this section. Okay, so we're talking about transformations. That's the general idea of this section. We're going to have these parent functions, and then we're going to transform them into something else. They will still be a version of the original function, but they'll be a little different. Now, we're going to talk about 3 different types of transformations today. The first one that we're going to talk about is something called translation. It has nothing to do with language. A translation is simply when you take a graph, the parent function. Okay, so let me change that a little bit. When you take the parent function and you slide it left, right, or up and down. Okay, these things consequently are sometimes called slides because you're just sliding the parent function around. What a translation really is, another way to think about it, is change in position. It would be like putting you in a different seat in the room, right? You're the same shape, you're the same size. Okay. We would just put you in a different place. That's the way to think of a translation. It's just a change in position, nothing else. Okay, I want to talk about something that we talked about when we did step functions a little bit. Okay, so I'm going to have this in here, and I want to talk about 2 different examples because this is going to come into play with, you don't need to write this down, but I want you to pay attention. Okay, so we talked about a graph like this last week, and then we also had a step function like this. Okay, and the reason that I want to bring this up, you'll find out in a minute, okay? When I made a table for this step function over here, what did this 2 impact? What 2 on the outside, what did it impact?
It was gonna
The slope?
The size of the step. No, this did not affect the size of the step. The what? It gave us all even integers, okay? So when it gave us all even integers, was that affecting the x or was that affecting the y? It was affecting the y because we were over here saying even integers. Okay, so this number on the outside affected the y. Okay, ooh, there's supposed to be a 1 here. My bad. All right. Now, we talked about this number on the inside. What did this 3 impact?
The size, it would be 1/3.
What would be 1/3?
The step.
The step would only be 1/3 wide. So this inside number now affected the x, because we would then need to go by the reciprocal, right? We learned that last week. So the point I'm trying to make is here, when I have a number outside, it affects the y. When I have a number inside, it affects the x. And that's going to be a theme that we're going to use throughout the rest of this lesson today, okay? That inside-outside thing. Now, when we talk about a vertical translation, a vertical slide, an up or down slide, when the constant, some number, is added or subtracted outside of the x term. And what we're trying to say here, what I'm trying to say, so what I'm trying to say here is based off of what we did on the other slide was that outside affects the y. Okay, when we have a number on the outside, we have a change outside of the x term, like we did on that last example, it affected the y. That 2 in front of the step function notation, the greatest integer function notation, meant that the y could only be even integers. It affected the y's. So if I have a number outside of the x term, in some cases it's going to be really clear, in some cases it's not, and I'll explain that. Then you should be able to tell just from the numbers what's going to happen to the parent function. So even before you graph, you should know what's going to happen to the parent function. And that should give you an idea of whether or not your graph is right. Now I'm going to give you some examples I'm going to give you 3 examples of ones that are outside types of problems. Here are 3 examples. Okay. First we have f of x equals x squared plus 7. Then we have g of x equals the absolute value of x minus 3. Then we have h of x equals x plus 9. And this one's kind of a special one, and I'll talk about that one here in a second. Go ahead and get those down, and then I'm going to talk about what you're going to be doing in your homework today and what I'm expecting you to do. So in this, for f of x, the parent function is y equals x squared, an original parabola. Okay? When I say it's outside, it's because the x is being squared, but the 7 is not. So there's something happening to the x. The plus 7 is happening outside of the x squared. That tells me that this plus 7 is going to affect the y. And so that means it's going to go up or down. And so intuitively, we have a sense of what's going to happen. What does this plus 7 mean the parent function is going to do? Where's it going to go? Up. How many? It's going up 7. This is the description. Okay? So when you're asked, how is the parent function transformed? You just say up 7. You could say the parent function moves up 7. I don't care. Same idea. And in a visual way to think about it, and I'm just going to draw a quick sketch. You can draw this if you want, okay? But you don't have to. That was terrible. All right, so here's my parent function, y equals x squared. There's the parent function. Okay? The transformation is just going to be, all right, I got to go up 7. And so the new function basically just looks like that. If those were the same shape, which obviously they aren't, they're supposed to be. I did a bad job. Okay, you get what I'm saying though? Okay, what you're going to do in your homework is just draw the transformation. You do not need to draw the parent function. But when you look at this equation now, you could be like, okay, I know what it's supposed to look like. I just have to change its position and move it up 7. All right, so what's going to happen with this absolute value? We know it's a v. This minus 3 says it's going to do what? It's going to go down 3. So that's all you need to do in describing the transformation. Again, in your homework, you have to describe the transformation 1, graph the transformation 2. So you're going to have to graph it. Now, when you go to graph it, does it have to be a perfect, graph with 17 points on it? No. It can be a sketch. You might have to draw a couple points just to get the feel for it, especially when we move on to some of the other transformations. But that's what you're going to be doing today, okay? We're going to consider this one outside for now, and I'm going to come back to it in a minute. So this would mean the parent function, the identity function, is going to go where? Up 9. So that's essentially the vertical translations when it's on the outside. The outside is when you know that it's up or down.
So
You're going to describe it, and then in your homework you're going to graph it too. Yep. Okay. All right. Next, let's talk about the inside. Think about what happened with the inside one before. So again, thinking back to the step functions, when that number was on the inside of the greatest integer function notation, it affected the x. So when we have an inside number, it's going to be a horizontal change. The difference is what we just did, it moved in the same way we expected it to. Plus 7 meant up 7. Minus 3 meant down 3. Now when it's inside, it's going to move in the opposite direction, so it's less intuitive. And this left or right means it's going to affect the x. That's why it's a horizontal slide. Now the inside slides, the inside moves are going to be a lot more noticeable than the outside ones. There's going to be parentheses a lot of the time, grouping symbols, could be greatest integer function, could be absolute value. It's going to be easier to recognize the inside than it is the outside. So here's a couple examples. So see what I'm saying? It's obvious that it's inside. There's a set of parentheses. The -5 is inside with the x. The +2 is inside with the x inside the absolute value. So that inside idea tells you that it's going to be a slide to the right or to the left instead of an up or down. Again, just be careful, because even though we see a -5 and intuitively we think -5 is to the left, inside is the opposite direction. So this actually is going to move right 5. And again, this is x squared, so it's a parabola. So the parabola is the parent function. It's going to just slide to the right 5 units. It's a change in position. This absolute value, and you had some of these on your quiz, okay? This means it's going to move left 2, okay? So again, these are the descriptions of the transformation of the parent function. This is what happens to the parent function to end up with our resulting transformation, okay? That's the first type of transformation. Any questions so far?
How do we graph them?
So, well, I mean, like this one. I'll do this one really quickly, easily, right? Right. We know that again, you don't have to. One, you can always make a table of points and do it that way. But we really are trying to get the idea here of like, if this is the absolute value function, this is the parent function of the absolute value function. This is the equation y equals absolute value of x. That's what it's supposed to be, okay? Now, all I'm going to do now is take this function, since this is an absolute value function, it moves left 2, I'm literally just going to move it over 2. And so the sort of notch of the v goes over here now. And so this would be the transformation.
So do we have to graph the parent one?
You do not have to graph the parent one, no. You can if you want, sure. You don't have to. But again, the reason I did is to show you how the numbers affect the transformation. On to the next one. So the next type of transformation is reflection, also known as a flip. You can use the words in it interchangeably, I don't care. Okay, just the same way that you can use the words translation and slide interchangeably. You have to know translation because in the book it's going to put it that way. You have to know reflection because in the book it's going to put it that way. But if you just tell me it's a flip, that's fine. Now, in our course, we're only going to talk about 2 types of reflections. There are more, but we are only going to talk about 2 of them. The 2 of them that we're going to talk about is a flip over the x-axis or a flip over the y-axis. When you get to pre-calc, you will learn about other types of reflections. But today is not that day. When something flips over the x-axis, it is known as a vertical flip. When something flips over the y-axis, it is a horizontal flip. Sometimes you'll see it written as, instead of saying a flip over the x-axis, it'll say something like flip about the x-axis. Same with the y-axis. Sometimes it'll be a flip about the y-axis instead of over. They'll use that word about in there instead of over sometimes. Now I'll give you a quick example. Let's see. Let me draw let's try this thing. Let's draw a triangle. There we go. Beautiful triangle, right? So if I flip it over the x-axis, okay, what's going to happen to it? Let's see if I can do this. Okay. It's going to go like that, right? Now, that being said, I'm going to put it back in its place. and give you a better idea. Like here's the x-axis, right? So when I flip it over the x-axis, it's going to look like that, right? So it literally flips over the x-axis. So because this is the x-axis, this changed vertically, right? Now, I could do the same thing with the y-axis, and this is, you're going to find maybe interesting. If there's the y-axis, and I take this triangle and I flip it over the, actually I need to duplicate it first. Okay, watch what happens when I flip it over the y-axis.
It looks the same.
Right? Did it change?
No.
Didn't change at all. I mean, it's not a perfectly, legit triangle. I mean, it's a legit triangle. It's not equilateral. It's not isosceles. But it basically is the same, right? But if I flip it over the y-axis, that's why it is a horizontal flip, because it flipped from side to side. Anyway, those are the two examples. Now, let me show you what they look like and how you can tell by looking at the numbers what happened. Okay? So you're looking for negative symbols now. You're looking for a negative. If the negative is outside, we're sticking with that inside-outside idea. If the negative is outside the x, then it flips over the x-axis. Now, again, the outside the x part is sometimes harder to tell than the inside. So here are two examples of the outside. Right, this one's easy to tell. I've got, absolute value here, and the negative is on the outside. Okay, so that's going to take that v and flip it upside down. This one will get you sometimes, right? And the reason I wrote it like this is quite simple. This negative is not being squared. If they wanted this negative to be squared, what would they have done differently? Yeah, they would have put parentheses around the negative and the x to indicate everything was being squared. I want you to make sure that you understand that there's kind of a big gap in between the negative and the x squared. The negative is not being squared. Only the x is being squared. So if you need to think about there's this big space in between the minus and the x squared, think about that. That's how I know that it's outside, because what's happening in this problem is squaring. Since the x is the only thing being squared, the negative is outside of that squaring. Okay? Now, so again, what would happen, I'm going to draw you just a real quick sketch. Okay? So here's the parent function. The parent function is going to look like this. When I flip it over the x-axis, you can be confident and know that it's going to look like that. Again, in your homework today, you're only going to have to draw the transformation. But if you wanted to know, you want to be sure that's what it would look like. Over here, the same idea. I would have this, and my parent function is a parabola. It looks something like that. Because of that minus on the outside, it's going to flip it over the x-axis. It's going to look like that. Okay? Again, in your homework today, you only have to graph the transformation. But if you want to picture these in your mind and think, all right, what is that negative on the outside going to do? You can get a good picture, because you should know that it's going to flip over the x-axis. Now, one of the things that gets tricky, now the inside is going to be easy to tell, but some of the transformations in terms of descriptions can be interesting, and I want to make sure we're clear on this. Okay. So, if the negative is inside the x, then it flips over the y-axis. Here are two examples. Okay, both inside, obvious inside. I've got the negative inside the absolute value. I've got the negative now inside the squaring. Okay, so what's going to happen? Here's what happens every year. Okay, and we talked about it a little bit. If I have, I'm going to draw a quick sketch, and I'm going to see if you can figure out what I'm trying to do. And hopefully I draw it perfect. It's already not perfect. Okay. Should we use the parabola or absolute value? What do you think? You tell me.
Absolute value.
Absolute value. Okay. All right. Here's the hopefully, the perfect parent function. Is that perfect? No, it is not. But we're going to take it, okay? Now, if I flip this over the y-axis, is it going to change? Okay. Let's see. Let's see if I can flip it over the y-axis. Ready? I'm going to flip it from the right to left. Ready? Did it change?
No.
No, I mean it changed because my drawing's bad, but it's really the same. Okay? So I can keep flipping it over the y-axis, it doesn't change. Now, here's where we run into trouble. Okay? While the graph doesn't actually look different, a reflection happened, right? I'm reflecting it. I did a reflection over the y-axis, even though the graph doesn't change. So when you go to your description, don't say nothing happened, it didn't change. Don't say that, because we did still reflect it over the y-axis. And it's important to understand that sometimes when you reflect it over the y-axis, the graph isn't going to change. But the reflection still happened. So you still have to say that it happened. I don't want you to mess that up. Okay? So even though it flips and basically doesn't change, it still flips.
So when it asks for like what happens, should you say reflect?
Yes, you should still say reflection over the y-axis. Now, that's only for these two examples, okay? There are other ones where you can reflect over the y-axis and it will obviously change. But in these two examples, they won't. The same thing would be true with a parabola. Okay, if I put the parabola on here, oh, that was bad. Okay, the same thing's going to happen for this particular example. When I flip it over the axis, it doesn't really change. It changes because my drawing's bad. But you get my point, okay? You still have to say reflection over the y-axis. Don't forget about that. All right. Or flip over the y. Last one, dilation. Dilation is when a parent function is stretched or compressed. Now that can happen vertically or that can happen horizontally. That being said, in our class, we're only going to talk about vertical stretches or vertical compressions. In pre-calculus, you will learn about horizontal stretches and horizontal compressions. In our class, we're only going to use vertical ones. Okay? But I want you to be aware, because sometimes in the book, if you're looking at answers, sometimes you'll see something about horizontal. So I'm going to talk about that a little bit today, but it's not my expectation that you use that verbiage at all. Now this is kind of the thing when, you put an image. I know Charlie was working on a presentation for one of her classes, and you put images in your presentations, right? Or you're making a slideshow or whatever, and you want to make the image bigger, or you want to shrink it down and make it smaller, that kind of thing. That's what we're talking about with the dilation. There's a slight difference, because normally when you change the image in your presentations, you keep the shape exactly the same, you just make the whole thing bigger or the whole thing smaller. With a dilation, that's usually not going to happen. We're only going to make the verticalness of it change, make it either taller and skinnier or shorter and fatter. So the shape is going to change in size a little bit, and it's going to change the way it looks as well. That's what's going to happen in dilation. So there's two different things that we need to know, and we have to pay attention to in order to determine how those numbers are going to affect the shape. So first off, when we're multiplying by a number, when we multiply x by a number greater than 1, then the graph is going to be stretched vertically. It's going to look like you're pulling it upwards from the top and stretching it out, making it skinnier. I'm going to put some graphs up here. I don't want you to take pictures of them. Just draw a sketch, okay? Just draw a sketch of these graphs. Here's the first graph. I know it's small, so let me write in what this equation is. This is the parent function y equals x squared, okay? So right now, it's just 1 in front. Okay. When I multiply this by a number greater than 1, what's going to happen is this picture is going to look like it's going to get stretched out. So think of it this way. Think of grabbing a hold of the top of this graph and just pulling it upwards. And this bottom, this vertex, is anchored. So this isn't going to move anywhere. But if I grab the top and pull it up, while this is still anchored, it's going to get skinnier. Okay, and so here's an example of that. This equation here is y equals 5x squared. So notice here, the viewing window is exactly the same. Nothing changed in the viewing window. But if I take this and pull it straight upward with the vertex anchored, it gets skinnier. And the reason why that happens is that the y values are increasing more quickly. So, for example, when I have 1 plugged in here, I get 1. But now when I plug 1 in here, it jumps to 5. When I plug 2 in here, I get 4. Well, when I plug 2 in here, it goes to 20. So the y values grow faster, which makes the graph look skinnier. Okay, so this is the transformation. This 5 transforms the parent function into looking like a skinnier graph. And here's, evidence I put them together. Okay, so here's the parent function. If I pulled it up, I would end up with this. Now we have to describe it. Here's how you describe the transformation. We say that it is stretched vertically, or you could say vertically stretched, either way, by a factor of 5. That's how we write it. When you describe the transformation, you just say stretched vertically or vertically stretched by a factor of 5. Either one is fine. Okay? But you're describing what you know that the parent function is being multiplied by, and that's how you describe that transformation.
Where did you get the 5 from again?
I made the problem up. Yeah, I made the problem up. Now, here's where, sometimes in the book, it'll say something a little different. It'll say compressed horizontally, meaning if you pushed on the outside of the red and you shoved it in and smushed it, that's what a compression is, a smushing. It's a very technical term, smushing. When you smush it in from the right and you smush it in from the left, it gets skinnier, right? So sometimes you'll see something that says horizontal compression. That's the same thing as a vertical stretch, okay? Just so you know that that's going to happen. Now, let's talk about a vertical compression. When I would take this parent function and smush it down, okay? Here's how that happens. That happens when you multiply by a number greater than 0 but less than 1. Well, that's what we would just call a normal fraction. If it's being multiplied by a normal fraction, and I say normal because we have improper fractions, right? That's not what we're talking about here. We have mixed numbers, which are part whole number, part fraction. I'm not talking about that either. I'm talking about a normal fraction. 1/2, 2/3, 7/8. And there's obviously an infinite number of fractions that you could come up with between 0 and 1. But that's what we're talking about here. If your x term is being multiplied by a fraction, that's where we get the vertical compression. And if we think about it in terms of how fast the y is growing, the fraction in front of that x term is just going to make the y grow more slowly. Therefore, it's going to appear fatter. So I'm going to use the same parent function. I'm going to use the quadratic, that y equals x squared. And this time, and I'll write this bigger so you can see it, this is the graph of y equals 1/4 x squared. Right? The 1/4 is obviously between 0 and 1. It's a normal fraction. Okay? And notice how it looks fatter, as I just described. So the y values climb more slowly because every time I plug an x in, it gets multiplied by 1/4, which makes the number smaller. So that's why it looks fatter. So again, here's the way to think about the vertical compression. I'm going to put them both on top of each other. Again, you can just draw a sketch. So if we think again of the vertex being anchored, the red is the parent. If I push down on the top of it, it's going to make it flare out. So that's why we call this a vertical compression. And so my description again would be something like this. Compressed vertically by a factor of 1/4. So the structure is the same, right? We said stretched vertically before by a factor of. Now we're saying compressed vertically by a factor of. You could say vertically compressed by a factor. It's the same thing. You could switch these words around and it means the same thing. Again, if you see the horizontal, the horizontal would be a horizontal stretch because now we're pulling it apart to get out here. All right, so if you ever see that in the book, that's what that means. All right. But again, in here, we're just going to worry about vertical. Vertical stretches, vertical compressions. Okay. So in your homework again today, what's going to happen is you're going to look at the equation that they're giving, and you're going to say, all right, what do the numbers do to the parent function? And then based off of that, okay, one, you're going to describe it and say, okay, it's going to go up 5, or it's going to flip over the x-axis, or it's going to be vertically stretched by a factor of 3, whatever that is. And then you're going to sketch that, okay? You can sketch it. It doesn't have to be a perfect, I don't need a giant table of values for every transformation, but you may want a couple points just to get the feel for it. And then you should get an idea like, okay, it said it was going to go up 3. Did it actually? Is that what I have graphed on my paper? Is it a parabola that moved up 3? And if it is, then you know you did it right. You know, if it's supposed to be a flip over the x-axis and it's facing a different way, then that's, you know, you obviously did something wrong. The other thing that you have to keep in mind is all 3 of these types of transformation can be used together. They don't have to be separate. You can have a flip and a slide and a dilation to a parent function. That's literally every linear equation. That's literally every parabola. Okay? It gets multiplied by something, it gets divided by something, something gets added to it, subtracted from it, whatever. And that's the basis of all the other functions that you know of.